Okay, folks, the 5354 homework is due tomorrow, and those were the big two sections. I mean, 5.1 was all the basic identities that we should know well by now. And if we don't know those ones well, we are going to struggle this whole chapter. We've got to know those basic ones from 5.1. 5.2 then got us into the proving of the identities, and then 5.3 were the sum and difference identities, and 5.4 were the multiple angle identities. If I have a double angle, a half angle, and the power reducers as well. So 5.3 and 5.4 were the big two sections that we've hit so far. We'll go ahead, we'll take a couple questions off of this homework assignment right now. I'm not going to do two of the proofs, though. I will do one proof and one from the front. So do we have one from the front we would like to look at, majority rules? I've got 5 in the mix. Anything else from the front? 5, I've got 6, I've got 2, I've got 8. We're going to have a split. 5, 2, 6, and 8. 2, show of hands for 2. I got 2, 2. Show of hand on 5. 1, 2, I got 2, 5. Show of hands on 6. I got 3, 6. Show of hands for 8. I got a show of hand. I got 5, 8. So we'll take a look at 8. Okay, so 8 is solving an equation. I've got sine squared of x over 2 and sine squared of x. What is the issue with number 8? Exactly. I've got over on the left-hand side, x over 2, or 1/2 of x, and on the right side, I've got x. If I'm going to solve a trig equation, the main priority is that I must have what? Same angles. I've got to have the same angles. Well, sine 1/2 x, is there something I can do with sine 1/2 x, or is there something I can do with sine x? There's something I can do with sine x. And first and foremost here, we've got to understand the notation. Sine squared of 1/2 x really means what? I mean, this is mathematical shorthand, but if you had to type that into a calculator, how do you type that in? Parentheses, sine of 1/2 x squared equals sine squared x. There's nothing I can do over here with the sine squared x, but there is something I can do with the sine 1/2 x. What does sine 1/2 x equal to? No. It's plus minus radical 1 minus cosine x divided by 2. Squared equals sine squared x. Problem alleviated? Yes. What is the only angle we have now? X. So that issue has been taken care of. And what also is going to get taken care of here now as well? The square is going to cancel out the square root and leave me with what? 1 minus cosine x over 2 equaling. So what's the other issue that's brought about now then? Two different trig functions. Are we going to have to deal with it, or can we make a substitution again? We can make a substitution. We can turn a sine squared into a cosine. What is sine squared? 1 minus cosine squared x. Pythagorean identity. And if we've got a fraction over there on the left, how about we make this a fraction as well, over 1. We now have a proportion. All my trig functions are the same. All my angles are the same. How do we deal with a proportion? So 2 minus 2 cosine squared x is going to be equal to 1 minus cosine x, right? We recognize that we now have a what? Quadratic. We now have a quadratic because of the squared. We now have a quadratic. What do we want to set this equal to then? 0. So I want to move everything left or everything right? I would say move everything right. Make it positive. So that's going to come across as 2 cosine squared x. We already have a negative cosine x. And if we're going to bring that 2 across, it's going to become minus 1 equals 0. And now we've got 3 different paths we could take. What's the quickest and easiest way to solve a quadratic if possible? Factoring, which in this case we could. If we can't factor, we can always use that's factoring. Quadratic formula or completing the square. Quadratic formula or completing the square. So let's go ahead and look at factoring this. One's going to have to be a 2 cosine x. The other one just a cosine x. Signs are going to be what though? Signs are going to be different, but the only thing that multiplies to 1 is what? So 1 and 1. It's just where do I put the plus and where do I put the minus? Well, we need a negative cosine x. So this one is got to be plus. This one's going to be minus. So this is going to give me negative 2 plus 1. Negative 2 plus 1 is the negative 1. Okay. So tell me then, what is this cosine x over here equal to? Negative 1/2. Can that happen? Absolutely it can happen. What is this cosine x equal to? Can that happen? Absolutely that can happen. Tell me what cosine looks like. Starts at max, down through and back up, right? So where's cosine x equal to 1? At 0 and at 2 pi. Okay, so x equals, and are we counting 2 pi on this one? We are not. Find all solutions in the interval 0 included to 2 pi not included. So x just simply equals 0 right here. 1/2, well that's one of our special values. We need to know where cosine is equal to 1/2. But where's cosine negative? 2 and 3. What's our reference angle? Where is cosine 1/2? It's a 60-degree angle. Pi over 3. Okay, so how do I put reference into 2? 180 minus. If it's degrees, but I want radian. Pi minus. So if I have 1 and I'm going to subtract off 1/3, I'm left with 2/3. 2 pi over 3 is our x value in quadrant 2. How do I go into 3? We add to pi, right? So what's a whole plus 1/3? 4/3. X equals 4/3 pi. Pi in quadrant 3. Okay. So we've got x equals 0, x equals 2 pi over 3, and x equals, what are we going to do with all 3 of those solutions? Yeah, we're going to go back and we're going to check them. We're going to go back through and check them. Okay. But this one here, again, 2 identity changes here, the 1/2 angle, and then the Pythagorean identity. Now I have a quadratic. I factor the quadratic. I solve it down through. All right, with 8. All right, with 8. Which choice is that then? D. Okay, so choice D. 8. How about on the back? Is there an identity out on the back I want to look at? And if there's no identities on the back, we can look at another one on the front. I'm fine with that. I just didn't want to do both identities because those are kind of where you guys need to do your thinking. Any identities on the back? Austin? Number 9? Any other ones thrown in? 13? Anything else? 9 and 13? Okay, so give me a show of hands for 9. 1, 2, 3, 4. Show of hands for 13. 13. All right, so over here we got a sine cubed of 3x, 1/2 the sine of 3x, and 1 minus the cosine of 6x. Well, I've got two different angles up there. I've got what and what? 3x's and 6x's. Well, I've got two 3x's and just one 6x. Could I somehow get the 6x to be a 3x? Absolutely I could. 6x is what plus what? 3x plus 3x. And then everything would be 3x. So let me start over here on the left. And we're going to say that that's still a factor of 1/2, a factor of sine 3x. And then we're going to shift this to be 1 minus cosine of 3x plus 3x. Which again is ultimately what? 6x. Now again here folks, always keep in mind your goal. What are we trying to get over on the right-hand side to be, or left-hand side to be equal to? Sine cubed of 3x, which means I have three factors of what? Sine 3x. Well, do I already have one factor of sine 3x over there? Yes, I do. So with this right here, I'm hoping to get numerically a what? A what? A factor of 2. Why do I want a factor of 2? Is there a numeric coefficient over here, folks? Is there a numeric coefficient over here? What is it? Why do I need to get a 2 out of here? To cancel that 1/2, right? So inside of here, there needs to be a factor of 2 to cancel out that 1/2, and then what else? A sine squared of 3x. I need 2 sine 3x's out of here. Because again, what is the 2 and the 1/2 going to do? Cancel, and then I'd have a sine 3x, and sine 3x. So in here, I need to get that out of it. Okay? We're looking at our goal. We're trying to see what we want. Okay? Well, I can definitely do something right there. Do we have an identity for the cosine of the sum of two angles? Absolutely we do. So 1/2 sine 3x one minus what? What's that? Cosine 3x, cosine 3x, or cosine squared 3x, plus or minus? Minus sine 3x, or sine squared 3x. Good? And again, all the work is still done inside of there. How do I get rid of that inside parentheses? Distribute what? The negative. So that becomes 1 minus cosine 3x plus sine squared 3x. And that'll take care of those inside ones. Now what? Sorry. What's that? Sorry, Austin. Doing too much. So what are you recognizing here? You see it a Pythagorean, right? He's got 1 minus a trig function squared. 1 minus cosine squared is what, folks? Sine squared. 1/2 sine 3x. 1 minus cosine squared is sine squared. Well, sine squared what? 3x. Plus sine squared 3x. How many sine squared 3x do we have? We have 2. 1/2 sine 3x. 2 sine squared 3x. Did we find the factors we were looking for? What's 1/2 of 2? 1. Sine 3x times sine squared 3x is sine cubed 3x. Have we proven our identity? Yes. Yes. Okay. So this was good. This is part of what we want over here. We just want 2 more of them and a 2 to cancel that out. Well, we found the 2 to cancel that out when we were able to make that Pythagorean substitution right there. What I was hoping you guys would say, and I'm glad you didn't because it can't be done, but I was hoping you were going to realize, oh, sine squared plus cosine squared. But is it a positive cosine squared? No, it's not. So I'm glad, Parker, that you realized the 1 minus out at the beginning first. Okay. 1 minus cosine squared is sine squared of that angle, which is 3x. So now we've got 2 of them. The 2 cancels the 1/2. We've got the sine cubed 3x. All right with 13? Good there? All right, very good. So when is this due then, folks? Yep, this is due tomorrow. This is due tomorrow. Boom. We want to get into we're going to get into 5.5, and all I'm going to do quickly here with 5.5 is have you recall for me what the law of sines is. What does the law of sines say? Side A over the sine of angle A is equal to side B over the sine of angle B, which is equal to side C over the sine of angle C. So yes, that is what the law of sines says, but how does it read? What the law of sines reads is that the proportion, or I'm sorry, not the proportion, but the ratio, what's a ratio? A fraction, yeah, it's a comparison of 2 things. It's a fraction. The ratio of any side of a triangle, and how do we label our sides? The lowercase. The ratio of any side of a triangle to the, what finishes the ratio? The side to the sine of the corresponding angle. The ratio of any side to the sine of its corresponding angle are all what? Are all going to be equal. Any side to the sine of its corresponding angle, that ratio will always be the same for all 3 corresponding side angle pairs. That ratio will always be the same. Okay? Now, where do we get our corresponding angle side pairs? So if I have side A, what is the corresponding angle for that? Directly across from it. Yep, it's directly across. Thank you. Okay, so angle A, we go across to get side A. Angle B, we go across to get side B. Okay, and the law of sines we found out was the easier one to work with, but what did it require in order to use it? An angle side pair. We had to have an angle side pair. So if all I knew was 3 sides, could I use the law of sines? No, we had to use the law of cosines to find the angles. Okay? If I have 2 sides and a non-included angle, 2 sides and a non-included angle, could I use law of sines? Absolutely can, right? Why? We have a side angle pair, right? But what was the issue with the donkey theorem? With law of sines. Now you remember the donkey theorem, right? The ASS, the side-side angle, angle-side-side, that's what we've got here, right? The donkey theorem. We could not use the donkey theorem to prove that two triangles were congruent. Can't use the angle side-side to prove the triangles were congruent. We found out why last year. We can use law of sines to find that angle, but, Austin, there might be two of them. Or there might not be one at all. This is the ambiguous case. This is the ambiguous case. We made the observation last year that we did want to use law of sines if we could. But we really didn't want to use it to find what? Angles. We didn't want to use it to find angles. Why? Because of the ambiguous case. Where is sines positive? Quadrants 1 and 2. What angles do quadrants 1 and 2 define? Where to where? 0 to 180. Well, if sine is positive in 1 and 2, which includes everything from 0 to 180, then there's two possible angles that we could get out of that. Okay? So we came across the ambiguous case question, and you saw it on your Regents exam last year. They wanted to know how many triangles can be constructed. And they gave you the option of 0, 1, 2, or 3. Which one could not happen? 3. You could not get 3. You could not get 3. But could you construct 2? Yeah, because there could be two possible angles. Could you construct 1? Yes, because maybe only one of those two angles worked. Could you get 0? Yes. If neither of them worked, you'd get 0. If neither of them worked. Now, how did we work them back to see if they did work? Okay? So I was given this angle. I came up here and I found this angle and both values that it could be. How did we determine if it was going to work or not? What's that? Not 180 minus the angle that we got. What did we do with the angle that we found and the angle that we already had? We added them together. And if it was less than what? If it was less than 180, it would work. Why? Because we'd have room for the third angle. But what if we added them together and got something that was greater than 180? It can't work. Two angles can't add up to more than 180. There wouldn't be a triangle. Okay. So we individually added both of them back to the original. So B1 plus A, was that less than 180? If so, yes, it works. And then we go to the second one, B2 plus angle A. If that one's less than 180, kudos to you, it works. Two triangles. If only one of them works, one triangle. If neither of them worked, no triangles. But could we ever get 3? No, we would not be able to get 3. Okay, so law of sines, very, very simple law to work with. Very easy to apply. But we've got to understand that the ambiguous case comes out of here as well. Ambiguous case with law of sines. And it's only if you're finding what? Only if you're finding an angle. Only if you're finding an angle. Okay, let's go and take a look at just a couple of the examples that they've done out of the text. Just to refresh you with using the law of sines. What does it mean when they say solve the triangle? Find everything. So what is everything in a triangle? 3 sides, 3 angles. So we should always, folks, we should always start with a diagram. We need a triangle. And they specifically called this triangle ABC. Does it matter how you label it? No. Absolutely not, as long as you're consistent. So where would side A be? Over here on the right. BC is side A. Where is side B? AC over here on the left, and side C is AB up on top. We know that angle A is 36 degrees. Angle B is 48 degrees. Side A is 8. Now, folks, right off the bat, if you're given two angles, you automatically get what? The third one. So 36 and 48. What's 48 and 2? 48 and 2 is 50. 50 and 4 is 54. 54 and 30 is 84. So we've got 84. What's 180 minus 84? What's 180 minus 80? 100. And then what's 100 minus 4? 96. So we got a 96 degree angle down here. What kind of a triangle do we have? Obtuse. We got an obtuse triangle, right? We've got an obtuse angle making this an obtuse triangle. Okay. Where's the largest side have to be? Why? Yep, the largest side is found opposite largest angle, triangle inequality. Okay, so we've got that third angle. Can we use law of sines? Yes, because we have a side angle pair. So we're going to start this off with what over what? 8 over the sine of 36. And I'm going to set up B and C all as one thing. 8 over the sine of 36 degrees is going to be equal to B over what? The sine of 48 degrees, which is also going to be equal to C over what? Sine of 96 degrees. You might as well set this all up at once. Okay, but first we're going to work with these two, and then we will work with those two. So tell me then, what will B be equal to? What times what divided by what? 8 sine 48 divided by sine 36. 8 sine 48 divided by sine 36. And now we go where? We go to our calculator. We make sure we're in what? Degree mode. Go ahead and do that for me as I'm setting up C. So C is going to be 8 sine 96 divided by sine 36. Nearest tenth, please. What did you get for B? 10.1? Okay, so go ahead and hit second enter and change your 48 degrees to a 96 degrees. Tell me what you get for side C. 13.5? Okay, and now make sense with this. Is it reasonable? And I mistakenly said the triangle inequality when I was talking about the angles. That has nothing to do with triangle inequality. Triangle inequality says that any two sides have to be greater than the third side. So 8 and 10, is that greater than 13? Yep, 8 and 13, is that greater than 10? 10 and 13, is that greater than 8? Can that work? Absolutely it can. So law of sines to find an angle. I'm sorry, a side. Very straightforward, using law of sines to find a side. Okay, let's try and hit a quick ambiguous case. Similar example then, again, solve the triangle. And I'm going to cheat. I'm going to use their diagram. Okay, side A is 7. Side B is 6. Angle A is 26.3. And we want to solve the triangle. Well, do we have two angles? We don't. We've only got one. Do we have the side that corresponds to that angle, though? Yes, we do. So we can use what? But we're going to be using law of sines to find what? An angle. Do we ultimately want to use law of sines to find an angle if we don't have to? No. But do I have a setup for law of cosines either? No. With law of cosines, I either need all three sides or two sides to the included angle. And I don't have that. So I've got to use law of sines here, and we've got to use it to find what? What are we going to be finding? Angle. Which angle are we going to be finding? Angle B. We're going to be finding angle B. So we're going to have 7 over sine of 26.3 degrees equal to 6 over sine B. So please tell me what sine B is equal to. 6 sine 26.3 degrees divided by 7. Tell me then what B will be equal to. Inverse sine of that monster right there. So we got to be very careful when we go into the calculator. First and foremost here, I need to check my mode, and I need to be in degree. And I will not do this all at once in my calculator. I will do 6 sine 26.3, and I'll go ahead and divide that by 7, and I'll get that, and then I'm going to go second sine, second enter. So I've got that. So B could be, what, 23 or 22.3? Or how do I find the other angle that it could be? 180 minus 157.7. Both of those angles have a sine of whatever it was. Both of those angles. And could both of those angles be an angle in the triangle? Absolutely they could. How do I test to see if they are? Okay, 22 and 26. Is that going to be less than 180? So there will be a third angle. 157 and 26. It's going to be close, right? It's going to be close. What do you get when you add them together? So the 0.3 makes that 158, right? 158. 158 and 20 is 178, right? And that takes it over. What was it? 184. Is that one going to work? Will not work. But do we completely scribble it out? No. Remember, just one line through it. It's part of the answer, but it just doesn't work. We had to reject it. So angle B could only be 22.3 degrees. So now can I find angle C? Yep. What's 180 minus the two of those? 180 minus the two of those. 131.4? 131.4 degrees. And now could I again do law of sines to find C again? Yes. Could we also use law of cosines now? Yes, but why would we? Law of sines is easier. So now, would I go back to this one or the B's? Go back to the ones we've got. So 7 over the sine of 26.3 degrees is going to be equal to C over the sine of 131.4 degrees, and then we'd be able to solve for side C as well. So ambiguous case. Remember working with it last year? Okay, we just got to be careful when we use the law of sines to find an angle. You got to be very careful with that. Looking through the rest of the section here, I don't think there's anything that is new to us. We're familiar with the law of sines. We actually did a different derivation for the law of sines last year. For us to derive the law of sines last year, we used the area formula, the K equals 1/2 AB sine C. And what we did is we divided them all by 1/2 ABC. So we divided everything by the same amount, which is completely legit. And what we ended up with then was a sine C over C, sine A over A, sine B over B. But all the areas have to be the same since it's the same triangle. So those ratios had to be the same. They've given you a little bit of a different proof here this year. Whichever one you prefer is fine with me. They're both very simple proofs. But we can use the law of sines to find anything in a triangle. We're very cautious of using the law of sines because of the ambiguous case with the donkey theorem. Whoops. Sorry, Charlie. We can handle the ambiguous case. We're all right with that. Applications, and we're kind of familiar with applications from all the Regents questions that we saw last year with these ones, but this one's a really good question because I believe Yeah, I think they're using kind of compass bearings on this one. Forest Ranger Chris Johnson and Ranger Station A sights a fire in the direction of 32 degrees east of north. So if they're measuring clockwise from due north, that's a course or a bearing. So it's really an easy question if you start off with this, but when you have to draw that, you've got to be very careful of it. So 32 degrees east of due north puts us right there. Over here at Fire Station B, we're 48 degrees west of due north. So can I figure out what these two angles down here are? Yes, they're complementary. Once I know those two angles, can I find angle C? Yep, so we'll know all three angles, and we know the two stations are 10 miles apart. Now can I use law of sines to find out how far we are away from the fire? Absolutely we could. Finding the height of a pole, so on and so forth. We'll take a look at the couple examples that are in your notes tomorrow. Because I don't want to double you up with a 5-5 when you've got the worksheet tonight, but tomorrow we'll be looking into the 5-5 assignment. Okay?
On Friday. If they return, there's signed permission slip from Mr. Butler before leaving today. Anyone who leaves early must attend the senior tea. Any questions, please see Mr. Butler or Ms. Kowalski. Any seniors planning on attending the junior-senior banquet this Friday night, May 15th, in the elementary cafeteria from 6 to 9 p.m., to sign up outside Mr. Butler's room. Swimming, basketball, kickball, and other games are available. Hot dogs, hamburgers, and other picnic food will be served. Seniors who work the Maple Festival go free. All others going, there will be a $10 charge. Attention juniors. Sign-up sheet for the junior-senior banquet is located in the main office. Today is your last day to sign up. Only those signed up and paid will be allowed to attend. Also, any junior that would like to sell beef jerky sticks to the class should go to the elementary school any day after school at Stevenson Farnell. Attention wrestlers. There will be a brief meeting this Wednesday during activity period in Mr. Palmetier's room to talk about summer wrestling. Anyone interested in wrestling next year is welcome to attend. If you can attend, please see Mr. Palmetier. If you haven't had a chance to order your copy of the 2015 edition of Pembroke Trails Yearbook, here is your opportunity. We have 15 copies left available on a first-come, first-served basis. The cost is still only $40, and you can order from Mr. Wangland in the art room. Hurry and reserve your copy before they're gone. Just a reminder, prom committee will be meeting today at the Woods at Bear Creek at 3 o'clock. Tickets for the Enchanted Forest prom will go on sale starting Wednesday. They can be purchased in the library for $35 single or $65 per couple. If you plan on bringing an out-of-district guest, make sure you turn in your approved form on time. Following students, please report to the office. Lucas Wesley, Renee Szymanski, Tiffany Finney, Sam Kellogg, and Lee Tingu. Thank you for your attention.
Okay, so you've got your worksheet to finish up tonight. We'll finalize 5.5 tomorrow. And then on Wednesday, we'll do our program for the law of sines. We'll do the program for law of sines. And there's actually going to be two programs for law of sines because we can use law of sines to find what? An angle or a side. Okay, so we'll do a calculator program, probably two calculator programs on Wednesday with the law of sines. Okay?